Hello everyone, and welcome to this first tutorial going through the machine learning workflow for underwater images that we're building at SUBSIM. So in this tutorial, I'll walk you through a step-by-step full workflow for training and testing a fish detection model on EDITO, which is this service, the European Digital Twin Ocean, using a small real-world data set that comes from images taken in Swedish coastal waters. So you'll train a lightweight detection model, inspect the results, and then compare it against a stronger pre-trained model. One important note before we start, this workflow is specific to the EDITO service, an application that we've built for this. The core SUBSIM workflow and notebooks in our GitHub repository are slightly different, so this tutorial is really about using a very accessible EDITO-based version of that workflow. Hopefully this gives you some insights into how all of this works if you don't have an extensive technical background, and we'll get started right away. So the first thing you want to do is to enter the Data Lab platform. You can also access this at datalab.dive.edito.eu. And I'm already logged in, but if it's your first time, you'll need to register an account and request resources. Once you've gotten those, you can find the SUBSIM app in the service catalog. The resources have already been set. This should be enough, and it's just to make sure that nothing goes slowly, you get no crashes while you're training. So just hit launch. All right. Then you just click this to copy the password, open the service, and then once you're logged in, it'll launch a Jupyter interactive session where we've already put everything that you're going to be using for this tutorial. So a little bit about this data set that we're going to be using today. The example we have here focuses on 3 fish species, including an invasive species, the round goby, Neogobius melanostomus. And the goal for this tutorial is to show the complete workflow from dataset to inference in a way that you can reuse later with your own data. So we have this README file that directs you through the playday. It's broken down into 5 different steps. So this should be the first thing that you read. And we'll start with step 1. So once you're inside, you download the playday data, and when you run this cell, you can run it using this play button, or you can do command return, and that will download and unzip the data into this notebook environment. So these 3 folders that you will be using. The structure is as follows. You can investigate it yourself and explore it. And your data set actually lives here. It's split into 3 different folders containing both your images and your labels. If you've already done a machine learning project, you'll know that the first step is generally annotation. So you're labeling your footage, and this is paired with your images. So you have your labels on one side, which are, for example, what type of organism it is, where it is on the image, and that is your finished data set. We also have a inference folder, which contains some images that we've prepared for you for today that your model will have never seen. And there's also a video that you can download to see how well it performs. And finally, the other thing you're downloading is this golden model that is a model that I've built that is fine-tuned as much as possible, essentially. So it's going to be ideally an upgraded version of the small lightweight model that you trained today, and you can play around with that one and also compare the performance. So there's 3 species in our data set. There is a golden wrasse right here, Goldsini wrasse, which is native, the black goby, which is also native, and this invasive species, the round goby. And it's a very invasive, damaging species which can outcompete other organisms in its environment, so early detection is very important. So let's move on to step 2, once you've explored a little bit on your own time. And this is the training notebook that you'll be using. So if you read the markdown, there's some very detailed instructions about what you do in this notebook and how it works. And it's broken down into 4 steps that you will run top to bottom. So what I'm going to do right now is a guided run through, essentially, where I show you what you're putting into the cells and some of the outputs, and then we'll talk about what is actually on your screen. So it's split into configuration, then you have setup checks, training, and finally your evaluation, where you look at the actual metrics and what they mean. So step 1, in phase 1, we configured a training run, and the main fields to look at, if you go back to the README, these are what you're going to be editing in the configuration. So your data path, you want to point to where your data set is. The easiest way to do so is to right-click on the actual file and hit copy path, but you can also write it manually, for example. You want to give your experiment a name that you'll remember, ideally. My first model is the suggested name. Next, your baseline weights. This is a base model that we're downloading from Ultralytics that your current model will be built upon, essentially. So this is kind of like a ready-made baseline that your model trains on, and it's made for object detection. So since our data set only has 100 images, we recommend starting with YOLO 11N, which stands for the nano version of YOLO 11. We'll also start with 20 epochs, which is enough to see the model learn without making the run too long, and it should be enough to get decent results. And I know there's a lot of complicated terms here, but if you scroll down to the bottom of this README, you have a glossary of the term, what it means, and why it matters, and there's also one within the notebook. Okay, so we'll just get started. What are you putting in this data path? As we've explained, this is where your data set goes. So your training runs, you don't need to edit this, but it'll create a folder called models, and this is where you can look at your runs. Next to your experiment name, we said we were calling it my first model, and baseline weights. If you want to mess around later with different models, for example, you can try the small model, the medium model. So these models are their orders of magnitudes bigger. So for example, if you have a small data set, 100 to 250 frames, I would generally recommend nano or small because larger models will overfit. If you have a medium data set, you can try medium, and so on and so forth. Okay, so we'll run the first cell. You can see that it's running here. And this should output the name of your data set, what your experiment is called, and your different parameters. This is simply a setup verification to make sure that it's ready to train. So once you've gotten the green check mark, you can head to phase 3, which is training your model. Now, for 20 epochs on 100 images, this should only take about 5 minutes, and you'll get kind of like a live table of what is going on. So we'll hit run for your training. So what this cell does is it loads your model and points it to your data set, and it starts the training using YOLO on Ultralytics. So as it runs, you'll see logs printed below the cell for each epoch. And the main thing to watch is how the training progresses over time, especially as your losses come down and the detection metrics improve. So for example, you have these 3 loss metrics, which are telling you how many of your objects are being seen, basically. And you want this to go as low as possible. You want this to decrease as you're training. So that's important to monitor. And the next 3 metrics that are important to monitor as well are your precision here, your recall, and your mean average precision at 50. And these you want to get as close to 1 as possible, which is essentially 100% accuracy. And these are telling you if it's finding the objects and if the training is going well. So I'm going to skip ahead here to the completed run so we can focus on the outputs rather than wait through the whole training process in real time. Okay, So training is now complete. You can imagine if you have a much bigger data set and you're training for more epochs, then it might take quite a lot longer, but this is quite fast. It took about 5 minutes, I would say. And just to reiterate, we did 20 epochs, and an epoch is one single complete pass on your training data set. So your Gobi dataset contains 100 images that are split into these 3 folders. One of them is the train, validate, and test folder. And the train folder contains the most images. It contains 70% of your images. And this is what your model learns. You have the valid folder, which contains 20 images, so 20% of your dataset. And this is what your model compares against while it's training. So once you set 50 epochs, it means that the model sees each image and label exactly 20 times if it's 20 epochs, or 50 times if it's 50 epochs. And this is while it's learning what's inside. So you can see that your results have been saved to models. Here we go. And this training step actually generates 2 models. So your last.pt is this last epoch, and the best.pt is the best checkpoint from the run and the one that you'll use for inference. So out of these 20, the best in terms of metrics and numbers, the best performing epoch will be the one that we use for analysis. So it's going to live right here. So after training, the first thing I would do is to look at the inputs. And one useful file is results.png. We'll zoom out a bit. And this shows the training curves across epochs. So if you've ever seen any publications, they would generally be showing something like this to say how well their training went, how well their model's performing. And what you can do is compare it with the training curves of the golden model. So this model was trained for 20 epochs. The golden model was trained for double. And you can see that there's some differences in the loss and these important metrics here. For example, in the golden model, this is a lot more similar to what we'd want to see. For example, this shape of a curve is not what you'd want. It means that you probably didn't go far enough in the training, so you'd want to increase the epochs. For the mean average precision, this is, I would say, the key metric when discussing model performance. You can see that it started to plateau potentially, but it was still increasing, so we'd want to train it for a little longer and see what happens. At 40 epochs, it was potentially decreasing, so you might not want to go further, but the whole point is that you're fine-tuning. So if the performance stops improving while training loss keeps going down, again, this is what you want to see for loss compared to some less marked curves. And if the performance stops improving while training loss keeps going down, it can be a sign of overfitting, which is quite common with small data sets. So this is something you need to learn and put in practice, which is fine-tuning. So once you've trained your model, phase 4, if you look in the README, is evaluation. So this is where we finally work with the test set, and this is 10 images. It's 10% generally, where you have images that your model's never seen during training, and you're trying to see if it's able to identify what's on those images properly. So it's a set of images it's never seen, and these would be the metrics that you publish because they're unbiased. So results, and they'll be saved in test eval. So you can also check out this folder. But these, again, are what you'd use if you're making, for example, a data publication, or if you're reporting on your model, how well it's performing. So the key metrics are precision, recall, MAP at 50 and MAP at 50 to 95. So precision tells you how many of the detections were actually correct. You want this as close to 1. Recall, we had it quite low at 0.4. This tells you how many of the real fish the model managed to find, so compared to your ground truth, how many the model found. MAP is just the standard summary metric for object detection performance. For a playdate like this, these numbers mainly help you understand the run and compare one experiment with another. So if you want, you can go back here and for example, change the nano model to a small model, and you can try to increase the epochs by 10 or 15, and then rerun it and compare both models. You also need to change the experiment name. For example, you can call it my second model and rerun it. Okay, so we'll go back to the README. We've already done step 3 now. And now we're going to take a look at what your model can actually detect on images it's never seen before. In the inference notebook, the two main settings are the model path and the images directory. So for the first pass, I'll point model path here to the model that we just made. So you go to models, go to my first model, and you need to find your best weights. This is the easiest way to do so, but you can also write it in manually. Okay, and your images directory is the one that we downloaded. So you go to inference, go to your Gobi images, and this is a set of 10 images that the model has never seen and that aren't in the data set whatsoever. So we'll copy that. There we go. Confidence threshold is set at 0.5, and then hit run. Okay. So 10 images. And when I run this, the notebook will load the model, process the new images, and it'll display detections with bounding boxes overlaid on each of the frames. So we'll run that. Here we go. Okay, and now you can actually see what the model detects and how confident it is. So this is the small model that we've made. It's not going to be perfect. As you see, there's a fish here that it wasn't able to detect, but here it's quite confident that this is our gold cine wrasse, and you have the confidence right here between 0 and 1. So the closer it is to 1, the more confident the model is that it's correct. So this is something you can go through and take a look at. And what I'd recommend, if you simply duplicate the notebook, instead of using the model that you've just built, you can try looking at the already fine-tuned model. So just copy this to get the weights of the fine-tuned model. And we're running it on the exact same set of images, so you don't need to change anything. So we'll run that. Boom. And then we're expecting this one to perform a little better in identifying fish. So if you compare the two, this one found 16 detections across the 10 images, and this one only found 7. Which means that maybe the data set needs more work, but in our case, the problem was that it wasn't trained for long enough, so it needed more epochs and probably more images. Comparing these outputs is a good way to see what more data and a larger model can buy you. In most cases, a model that's been fine-tuned and trained on more images and a larger model will be more stable, more confident, and better on harder detections. Like this one, for example, all you can see is the head of the fish, and I don't expect a model that's been trained. Oh, it did. Wow. But at significantly less confidence, essentially. But good. And this gives you a useful benchmark for understanding where your model stands and what you might need to improve. Another thing you can do is to lower the confidence threshold, which controls how sure the model needs to be before it shows a detection. If you put it quite high, for example, at 0.7, it will only show detections that it's more than 70% sure about. And if I lower it, I'll usually get more detections, but also more noise and more false positives. If you want to look at your false positives, you have this confusion matrix here, which can be a bit hard to decrypt. It's confusing, but it can give you information about what your model is mixing up. So if I look at the model that we just trained together, up, and then Gobius niger and Neogobius melanostomus are sometimes confused with the background, for example, and this is not a problem that we have in a model that's seen more images and has trained further. So this can explain why you see a difference in results, for example. Okay. One final practical note. And this will round off our tutorial. The SUBSIM environment in EDITO is temporary, which means that files stored only in this notebook session will disappear when the service shuts down. So if you want to keep your trained model or inference inputs, or if you want to play around with uploading your own data set and analyzing it, make sure to copy them to your EDITO personal storage. And this notebook includes a command for doing that. And you should be able to see it in your file explorer in EDITO. So that's the full workflow. We launched the service in EDITO and downloaded and inspected the dataset. Then we trained a small YOLO model to then evaluate it on a held-out split, and then ran inference on unseen images to compare our own model against a stronger golden model. The main takeaway is not just how you run the notebooks, but just for you to think about the overall pipeline, how your data should be structured, your choice of model, evaluation, inference, and comparison. These are all very important steps that can allow you to have a very robust model at the end of it. And from here, you can experiment on your own. And I wish you the best of luck. Thank you.